Hello and welcome to this tutorial after a long time. Today we'll be talking about DBSCAN clustering algorithm. Last time we talked about k-means, and we're gonna show you how DBSCAN is different from k-means and what are the underlying techniques while generating clusters following DBSCAN clustering algorithm. I am Abdul Al Safi, doing my master's in data and knowledge engineering, and currently I'm working as data scientist intern in an AI-based company. Alright, so first let's talk a little about what is DBSCAN. So DBSCAN is an algorithm which actually generates clusters based on density, and how it is done, how the algorithm finds the density over database elements. We'll find it shortly. And DBSCAN can generate random shaped clusters. Generated clusters can be of any shape, like triangular, rectangular. It can be of any shape. Yeah, the shape is not very much specified. And here another line is written: however, clusters that lie close to each other tend to belong to the same class. Let's bat an eye to the picture. If we look at database 1, all right, we see very well separated clusters here generated by DBSCAN. So what this line is trying to tell us is this cluster, these data points belong to the same class. These data points belong to the same class, these data points belong to the same class, and these data points belong to the same class. Okay, so what is class? We'll get to learn about this when we study about supervised learning. But for now, we can say using this property, using this evolutionary measurement, we can actually find the homogeneity property of our data. Yeah, that will be discovered in the later part. So before getting into the algorithm part, we have to understand and we have to get inside some definitions. First of all, the EPS neighborhood of point, mean PTS, core points, border points, noise points, directly density reachable, density connected. So these are the concepts we have to go through before we try to understand the algorithm. Yeah. So what is EPS neighborhood of a point? So let's say we have a point in our domain, and when will we say a point is within EPS neighborhood of another point? Let's say the test point is P and Q. The test points are P and Q. So we have to test that, we have to figure out that whether P is lying within Q's neighborhood, Q's EPS neighborhood or not. Yeah. So Q element of D is our data set or domain. So that if the distance between P and Q is less than or equal to some EPS value, which is to be specified by the user in the algorithm, so then we can say, all right, P is within neighborhood of Q. Okay, so this is the condition here. We have to set some EPS value, and if distance between 2 points is within that value or less than that, within that value, then we can say they are sharing neighborhood with each other. Yeah. Now, what is core point? A point is core point if that point has min PTS number of neighbors. And what is this min PTS here? It is actually another parameter specified by the user. And let's say in my algorithm I have specified 5. So imagine a point P, if it has 5 neighbors or more than 5 neighbors, then we can denote that point as a core point. Okay, this is very important concept. Now, border points. A point is border point if it does not have min PTS number of neighbors, let's say, but a border point shares neighborhood with at least one core point. That means a border point, yes, obviously from the name it cannot be a core point, but at least it is sharing its neighborhood with one of the core points in the domain. Yeah, this is very important point to be remembered here. It shares neighborhood with at least one core point. Yep. And then noise points. So a point which is not core point, which is not border point, it's simply a noise point. Okay, in other words, a point which does not share neighborhood with any of the core points, that's a noise point. Okay, we'll get more clear about these concepts when we'll see a mathematical problem in this slide. Till then, let's keep going. Alright, now what is directly density reachable? Now we know the definition of core point, border point, and noise point. So using these definitions, using these concepts, we will try to figure out that how each point is connected with other points in a cluster. And there are actually three ways of telling that story: directly density reachable, and density connected. Okay, so a point P is directly density reachable from a point Q. Very important. A point P is density reachable from point Q. From which point and to which point? That is the important concept to understand here. From point Q, a point P is directly density reachable from point Q with respect to EPS and mean PTS, that is the user defined parameters here. So a point P is density reachable from point Q if P belongs to the neighborhood of Q. Yeah, that means this condition that we studied earlier. Yeah, and Q has to be a core point. If P is directly density reachable from point Q, so this point has to be a core point first, and then P has to share its neighborhood with Q. Then we can say, alright, P is directly density reachable from point Q. Alright, then the next one. Oops, before that we can check the figure here I have set. As you can see, P and Q, P directly density reachable from Q, but Q is not directly density reachable from P. Why so? Because P is directly density reachable from Q because Q is a core point here. See, Q is sharing neighborhood with many points here. Let's say, let's imagine our mean PTS in this algorithm is 3, so Q is a core point, but clearly and surely P is not. So P is directly density reachable from Q, but Q is not directly density reachable from P because P is not a core point here. I think the concept is pretty much clear now. Alright, moving to the next one. Density reachable. So what's happening here? It's not very difficult to understand. A point P is density reachable from point Q with respect to EPS and mean blah 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 if there is a chain of points P1, P2, P3 ... Pn, and supposedly P1 is equal to Q and Pn is equal to P, such that Pi plus 1 is directly density reachable from Pi. Confused? Alright, let's make this easy for you people. We have a chain of points, let's say P1 to Pn. Yeah, to clear this more out, I will show this picture to you. Yeah, so we have we have chain of points P1 to Pn, and where I'm imagining P1 is equal to Q, from where I'm actually starting, and Pn is the last point up to which point all the up to which point Q is density. So we were saying P is density reachable from point Q, right? So Q is the point from where we are starting and considering whether P is density reachable from Q or not, right? So how it is happening, all these series of points have to be consecutively directly density reachable with each other. That means P2 is directly density reachable from P1, P3 is directly density reachable from P2, and so on and so forth. This is what this general structure says, that Pi plus 1 is directly density reachable from Pi. Alright, I think this is clear. Still we can see the picture here that if you see only 3 points are here as an example. Could be included, more points could be included, but yeah, let's consider this example. So P is density reachable from point Q, then again Q is the core point, and let's say this is this point. This point is S, let's imagine. So S is directly density reachable from Q, and then S to P. P is directly density reachable from S. So Q and S, both of them are core points here. This is clearly seen. If you see this boundary of the cluster and this boundary of the cluster, both of them are core points because they are sharing mean PTS number of neighborhoods. Yeah, but if you consider P, which is the last point, this is not a core point. So the last point here, which is Pn, this is not a core point, but except Pn, all the previous points which are consecutively directly density reachable with each other, all of them are core points, all of them. All right, okay, moving to the next one. So density connected. Yeah, so a point P is density connected to a point Q respect to EPS and mean PTS if there is a point O such that both P and Q are density reachable from O. So there is a point in the middle. Yeah, so P is density reachable from O and Q is also density reachable from O. So when such condition arises, we can say, all right, P and Q are density connected. And actually this is the main criteria here which is used to generate a final cluster, which is used to measure whether the density of a cluster or the density of data points in a specific region is enough to build a cluster or not. Alright, then moving to the next slide. Now we have enough knowledge of definitions to go through the DBSCAN algorithm. Yeah, so first of all, we label all the points as core, border, or noise point. We know how to do that. So now the second step is saying put an H among all core points that are within EPS of each other. That means there can be more than one core points sharing neighborhood with each other. Yeah, and we just draw an H among all the core points which are sharing EPS neighborhood with each other. Yeah, so make each group of connected core points, that's what I told you earlier, that connected density connected core points will be a final group to form a cluster. So that's what the third line is saying. Make each group of connected core points into a separate cluster. Now we are done with the core points. Now let's assign all the border points to one of the clusters of its associated core points. So each border point, they are associated with core points, right? So after we put age on all the connected core points, after that we start assigning border points to its corresponding core points. Yeah, I know this is a little confusing, but when we get into the mathematical problem, things will be clear, things will be more cleared out. Yeah, now if a point is noise point, just throw it away. This is the wonder, this is the the positive thing of DBSCAN algorithm, that you actually have some points in your dataset which does not belong to any of the clusters, and you just want to throw them away. If you remember from K-means algorithm, no data points were left behind. All the data points were included in all the clusters, right? Whether they would make sense or not, but we still would include them in any of the clusters. Yeah, but that's not a very optimal solution. The optimal solution would be to throw away those data points which are creating problems in the quality of a cluster. Okay, so we want good clusters, and there will always be some data in our data set that will try to ruin the quality of the cluster. Yeah, so DBSCAN is properly dealing with that fact. It's throwing away all the noise points, but however we can keep that as a reference to check different aspects of our data set. Yeah, we are however not including those noise points with our clusters, but still we can keep that to check different properties of our dataset, or homogeneity, let's say, or if there is any class imbalance problem in our dataset, and so on and so forth. Yeah. So finally, when all the instances are processed, our algorithm converges. Yeah. Now let's get into a sample problem and try to solve it. So we have this sample problem here where the value of EPS is 1.5, mean PDS 3, and we have 6 data points here. Yeah, as the same thing I say all the time, that this is very small data set. Yeah, 6 data sets, nothing. But when you are trying to solve a mathematical problem by writing, that's okay. That's okay to, like, when you are trying to clear out your skills, your intuitions, it's okay to deal with such number of data. It's not a problem. So the question asking me to put all these points as core, border, or noise point to find out what point is which point is what, and what are the resulting clusters here. All right, let's see. Okay, so this is my finding. I have calculated. Actually, we have to go through all the points, and we have to find out distance from all the point to all the point, from A to B, A to C, A to D, A to E, A to F. Then for B we do the same, C, D, E, we do the same. All right, I think that's understandable, and our objective function here is Euclidean distance. Yeah, so what was our EPS value? That was 1.5, and mean PDS was 3. Just to recall, what was EPS? This is the value when the distance between 2 points is less than or equal to this value, we can say those 2 points are sharing neighborhood with each other. And mean PTS, this is the number of neighbors, minimum number of neighbors a point should have in order to be a core point. Yeah, so I'll start from D. I'll start explaining from D. This is there is one interesting thing here, that we can see only 2 neighbors of D, right? E and F. That is within this EPS limit, and all the other values have exceeded this limit. But still I'm saying that, yeah, D is a core point. Can you say why so? Because there's one thing we consider here, and that is D is also sharing neighborhood with itself. I repeat, D is also sharing neighborhood with itself. That means D is sharing its neighborhood with E, with F, and with itself. So that makes total 3 neighbors. And our mean PTS value is also 3. So D is a core point because it has mean PTS number of neighbors in the domain. Alright? And E actually has 4 neighbors here with C, D, F, and itself. For F, again, it has 3 neighbors. So D, E, F, these are the core points in our problem. Now let's go back to C. What C is doing here? So C has, C has shared neighborhood with E and with itself. So it's not a core point surely, because it does not have mean PTS number of neighbors. But now we have to find out that whether it's a border point or not. If you remember how we define border point, a point is a border point which at least share neighborhood with one of the core points in the domain. And here C is sharing neighborhood with E, which is a core point in our domain. So C is a border point. And how came A and B are noise points in our domain? Because A is sharing neighborhood with B, B is sharing neighborhood with A, but none of them are core points. So A and B are sharing neighborhood with themselves, but none of them are core points. So yeah, it's pretty much obvious that they are noise points in our domain. So some findings we have figured out from our sample problem. The first one is an instance is always within neighborhood of itself. Yeah, that's what I said. And there can be more than one core point in a cluster, because many of you might get confused thinking that just like k-means clustering, where we had only one center, yeah, in a k-means cluster, but here in DBSCAN there is no center point of a cluster. And do not get confused considering core point as the center of a DBSCAN cluster. Okay, there can be thousands of core points in a cluster, in a DBSCAN cluster. So core point and for k-means center points, these two things are not the same. Yeah, so there can be more than one core point in a cluster. And if you are really, if you have already get pretty much familiar about the definition of core point, border point, and noise point, this finding is useless for you. But still, some of you might get confused when you see a point is sharing neighborhood with another point, but still it's a noise point. How? Because it's not sharing its neighborhood with a core point. A noise point can share neighborhood with another noise point. That's okay, as long as that the number of neighborhood for a point is not exceeding the min PTS limit, it will be a noise point, or it will be a border point if it's sharing neighborhood with one of the core points in our domain. Okay, now there was another question in our sample problem, and that was, what are the resulting clusters? All right, however, I'm not going to answer this in my PDF, in my presentation, so I'll expect you people to sort this out, and I want you people to write about this in the comment section of the group. So thanks for being here, and if you think that whatever I presented was not enough and you need some more reading, so click the link below, additional reading. And if you want to subscribe my channel, feel free, go there, check previous videos as well. There are some 2 or 1 demonstration of my work as well. Feel free to subscribe. And yeah, so next time I'll try to come up with an implementation and a data set with 66,000 records, and I'll try to apply DBSCAN clustering algorithm over that data set. And yeah, I hope that's gonna be very exciting. So till then, enjoy data science.